microwave antenna. Microwave antenna means the range of frequencies that are more than 3 gigahertz operating frequency. We will use this horn antenna. Okay, we'll discuss this horn antenna today. This horn antenna is the simplest micro antenna, we can say. This horn antenna is used as a feeding element, okay, or feeding antenna in dish antennas like parabolic reflector antennas. If you take in our homes also, we are having some small dish antennas, right? Okay, in that dish antennas, there is at the feeding point, we will use this horn antenna. Okay, we'll discuss the applications of horn antenna later. Here we can say that horn antenna is used as a feeding element, okay, in case of parabolic reflectors or dish antennas, okay, that are used for satellite communication or radio communication. Okay, now this horn antenna is a aperture antenna. Okay, earlier you have seen the antennas are there are wire antennas, but this horn antenna is having some aperture in the sense there are some area. Okay, how this horn antenna is manufactured is, first we'll take a waveguide. Okay, you, this waveguide can be flared. Flared means we can able to expand that waveguide in different x and y, x, y, and z directions. Okay, let us say in a Cartesian coordinate system, if you take a waveguide and we will do the flaring in all directions. Okay, like మనం దాన్ని సాగి కొడతారు అన్నమాట. Okay, దాన్ని మనం we can call it as a flaring in x and y directions. Okay, it will form the horn, and now we'll discuss the structure of horn antenna. Okay, how it will look like, or the operation of the horn antenna also in our coming slides. Okay, this horn antenna is having high directivity. Okay, because of the flaring, okay, it can able to receive more amount of electromagnetic energy, so that the directivity also will increase. Okay, and one more important thing is, because of this flaring, the waveguides are having a less impedance. Okay, around 50 ohms to 60 ohms maximum. Okay, we cannot able to radiate the electromagnetic energy using simple waveguide antenna. Okay, because of this flaring, okay, we can able to get the impedance of this horn antenna is equal to the free space impedance. What is the free space impedance? What is the free space impedance? The free space impedance is 125 or 377 ohms, right? Okay, because of this flaring, we can able to achieve the impedance matching. One more important point is this horn antennas, all horn antennas, they are directional antennas. Therefore, it's a directional antenna means, okay, this can be used for a long distance communication. Okay, this is about the basics of horn antenna. The structure of, you see that the structure of horn antenna, it is looks like this. Okay, the structure of the horn antenna is looks like this. Okay, see here, earlier this is a waveguide actually. Okay, let us say the length of this waveguide is A, and the breadth or width of this waveguide is, let us say, it's B. What we are doing is, okay, we are doing the flaring in the x and y and z directions. If we do the flaring, okay, we'll get this type of shape. Okay, normally the waveguide is having very less input impedance. Okay, this is around 50 plus or minus 10. Okay, you can say that 40 ohms to 60 ohms only, the maximum 60 ohms, the minimum 40 ohms. But the free space impedance, if you want to transmit the electromagnetic signals into the free space, if you want to radiate the electromagnetic signals, okay, the impedance should be matching. The impedance of the antenna and the impedance of the free space, that should be matched. Otherwise, it won't be able to radiate the electromagnetic energy. Okay, if you use simple one single waveguide, okay, this waveguide cannot able to radiate the electromagnetic energy into the free space. If you do the flaring means saagotadam any directions lo. Okay, we'll do the flaring. Okay, now the see the dimensions of this waveguide will become, see here, now the small a will become capital A. Okay, or I can written like this, no problem. Okay, ma. Now the dimensions are bigger. Okay, because of this flaring, the input impedance is increased. Okay, because of this, see, suppose if it is used as a as a receiving antenna, see, most of the electromagnetic energy will come to this point, and we can able to, from here you can able to connect to the amplifier, and you can do whatever is required. Okay, because of this flaring, the directivity is increased, and also the impedance also matching. Okay, what is the free space impedance? Is 377 ohms. Okay, in waveguides, okay, if the direction of propagation of the electromagnetic waves in this direction, okay, always the electric field is always in this direction, perpendicular to this direction of propagation, and H is in this direction. Okay, H is in this direction, E is in this direction, the wave will propagate in this direction. Okay, now okay, here because of this flaring, okay, here also there is some path difference is there. This is the cross-sectional view of the horn antenna. In this cross-sectional area, if you see, okay, here, let us say this is O, C, and B. Let us say this is the distance of L. Okay, I have not properly drawn this one. Okay, see here, this is the L, length of this L. Okay, here this is the path difference. Earlier we can say that path difference. Now we can say that this is the flaring distance. Delta E is the flaring distance, and theta E, this is the angle with the axis, and this OE, sorry, OC. This is the flaring angle. Okay, based on the flaring angle, we are getting the electromagnetic signals. We are getting the directivity also, beam width also. If you increase this flaring angle, the beam width also will increase. If you decrease the flaring angle, beam width also decreases. Okay, if you decrease the beam width, it has high directivity. If you increase the beam width, it has the low directivity. Okay, you already know that. Okay, you can say that clearly, the directivity is inversely proportional to the beam width, or the directivity is inversely proportional to the aperture area. This is the aperture. Okay, okay, this is the aperture. Okay, if it is having a higher aperture, then the directivity is very less. Okay, if it is having the less aperture area means the dimensions are less, then it is having high directivity. Okay, we already know that. Okay, here A is called the aperture area, and the length L is called the flaring length. Delta E is called the E flare, flaring distance. H also you can do. E in the sense it is vertical. Okay, this is the, see here. In this, if you do the flaring in this direction, this is E plane. Okay, if you do the flaring in this direction, this is H plane. Okay, don't confuse about that. Okay, now if you apply simple rule here, let us say, if you apply the Pythagoras principle here, what is the Pythagoras principle? Say that this is O. OB square plus CB square is equal to OC square. And also you can write, suppose this is the angle theta, right? What is the cos theta? Cos theta is equal to, what is the value of cos theta? If you want to write, see here, cos theta is equal to OB divided by OC. What is OB? This is the, okay, this is the OB divided by OC. OC is the diagonal, and this is the OB. Similarly, we can take the tan theta also. Okay, what is the tan theta value? Tan theta is equal to CB by OB. What is this? What is the CB? Suppose if the height of this is capital A, now CB will become A by 2. This OB is L. Okay, we substitute in this equation. Now we can write theta value. Just simply I have calculated this theta value. This is the flaring angle. Theta E is the flaring angle. E plane flaring angle. Okay, now you apply the Pythagoras theorem. You can say that what is the Pythagoras theorem says that OB square is OB square plus CB square is equal to OC square. What is the OB square? It's L square plus A by 2 square. That is equal to L plus delta E whole square. Okay. If you simplify this equation, okay, we are getting this is the formula. Okay, generally the flaring angle is very small. Okay, by neglecting this flaring angle square term, okay, delta E is small, delta E square very small. Okay, it is less than a very small value. That's why if you eliminate this delta E square term, okay, we will get a expression for the flaring length. Okay, L is the flaring length. This is the L. This is the L flaring length. The flaring length L is equal to A square divided by 8 into delta E. Delta E is called the flaring distance in E plane. Similarly, if you do the flaring in H direction, H direction means what? See here, this is the E direction, this is the H direction. If you do the flaring in this direction, okay, now the length of the flaring will become L is equal to B square divided by 8 into delta H. Delta E is the flaring distance in E plane. Delta H is the flaring distance in H plane. Okay. If you want to design a proper horn antenna, there is some limitation is there. That limitation is that the flaring distance in E plane should not be less, it will always be less than 0.25 lambda. And the flaring distance in H plane is always less than 0.4 lambda. Otherwise, you cannot able to radiate the electromagnetic energy into the free space. You have to remember this constraint. Okay, now, okay, here we can classify these horn antennas based on the flaring. Okay, if you do the flaring only in E direction, then it is called E plane horn. Okay, if you are doing the flaring in H direction, then it is called the H plane horn. Okay, if you are doing the flaring in both the directions, E plane and H plane, then it is called a pyramidal horn. Okay, okay, see here, these are the, I can able to see the differences in this picture. Here, this is the E plane. E plane means this is in this plane. If you do the flaring more in this direction, then the horn antenna looks like this. This is the waveguide. We are doing the flaring. Because of the flaring, we are getting this shape. This is E plane horn antenna. Okay, this if we suppose if we are doing in this direction, okay, this type of horn is called H plane. If you are doing both the directions, E plane and H plane, then it is called pyramidal horn. Okay, suppose if you take the circular waveguide and do the flaring, then we are getting the conical horn antenna. Okay, in some cases, we'll do the flaring on both the ends of the circular waveguide. This type of horn antenna is called biconical horn antenna. Okay, these are the different types of horn antennas that are used. Okay, here, if the flaring angle, okay, if the flaring angle is very large, what do you mean by that? If the flaring angle is very large means, if the flaring angle is very large means, okay, we are getting this theta E, actually this is theta E. If you take the total, this will become the 2 times of theta E. If the flaring angle is very high, it results the non-uniform phase distribution. Okay, non-uniform phase distribution. You want to see, I want to write here. Suppose if this is the waveguide. Suppose we are getting this is the cross-sectional view. Okay, because of this flaring, the electromagnetic waves will flare like this. Okay, because of this, see here, there is a non-uniform distribution and the beam width will be increased. Okay, if you increase the beam width, the directivity will be reduced. Okay, similarly, okay, if the flaring angle is too small, what do you mean by that? Flaring angle is too small means, suppose the flaring angle is like this. Now, it will emit the electromagnetic waves like this.